Today we're going to be looking at our Learning Target 2 from Unit 6, which is I can use numbers written in scientific notation to express how many times as much one is than the other. So before we can do this, we need to understand how to write numbers in scientific notation. So scientific notation is a method that we use to write very large numbers and very small numbers so that we're not writing 20 zeros or 30 zeros when we're talking about distances or anything else that might use very, very large numbers and very, very small numbers. So the format that we follow, there's 3 criteria that needs to be met. The first is that the first value in your scientific notation must be a number between 1 and 10. It can be 1, but it cannot be 10. So it has to be greater or equal to 1, but less than 10. So that's the first criteria that it needs to follow. The second criteria is that it should have times 10. So you take that first digit, we call those our significant digits, the numbers between 1 and 10, and then we need to make sure that it's being multiplied by 10. The third criteria is that we have an exponent attached to that 10. So it can either be a positive exponent or a negative exponent. So if we look at our little box here with recognizing numbers in scientific notation, if I look at that first box, I see that the first value that I have here is a number between 1 and 10. It's greater than 1, but it's less than 10. I do have the times 10 portion, and then I have my exponent. So we would say that yes, this is scientific notation because it follows all 3 criteria. If I look at the second box, we have 349 thousandths. 349 thousandths is not between 1 and 10. So right off the bat, I can see that this is not going to be scientific notation. For the third box, I have 5 times 10 to the 4th. 5 is between 0 and 10. We have times 10 included, and then we have an exponent of 4. So we would say yes, that is in the proper format. That is scientific notation. Box after that, we can see our first digit is between 1 and 10. We have times 10 to the power of 13. So yes, this is a number written in scientific notation. If we look at that first box in the second row, I can see my first digits are 3.67. That is between 1 and 10. However, if I look at the second portion, it's times 5 raised to the 10th. That times 5 is not part of our scientific notation criteria, so that is not a number written in scientific notation. If we look at the next box, 3.4, that's between 1 and 10. We have times 10 raised to the 9th power. So yes, this is scientific notation. If we look at the next one, our first digits, our first value is 13.045. 13 is not in between 1 and 10, so this is not scientific notation, or it's not written in proper scientific notation. In our last example, we have 1.05. That is between 1 and 10. We have times 10. Now this one, some people might say, nope, it doesn't have an exponent. However, remember, even if an exponent is not written there, we can always assume that there is a 1. So yes, this is proper scientific notation. So when we are converting numbers between scientific notation and standard form, we are going to use our exponents to help us decide how we are going to how we're going to convert between scientific notation and standard form. So if the exponent is positive, you're going to move the decimal to the right, the number that it says in the exponent, and if the exponent is negative, you are going to move the decimal to the left to convert to your standard form, which is the traditional way that we would write a number. So let's put this into practice. So writing standard form numbers in scientific notation. The first part that I need to do here is I need to remember that my first criteria is that I have a number that is between 1 and 10. So looking at this incredibly large number here, I know that if I want a number between 1 and 10, I need to focus on these digits here. And so I would put a decimal between 5 and 10. Okay, so I would look at my digits. I would put a decimal between 5 and 8 because that's going to give me a number that is between 1 and 10. 5.8 is between 1 and 10. I'm then going to look at how many places will the decimal have to move from where it is currently located at the end of the standard form number to get to the location between 5 and 8. And I'm going to use what we call swings. So if I start at that decimal at point at the end, I'm going to swing in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there are 17 swings that decimal has to move to get between the 5 and the 8. So according to our criteria, we have 5.8 is between 1 and 10. My second criteria is that I have to multiply by a power of 10, and my third criteria is that it is to an exponent, and this is where the number of swings comes into play. So however many swings you have is what your exponent is going to be. Okay? So if we look at number 2, I can see my decimal starts at the end of my number, and if I want to create a number that is between 1 and 10, my significant digits are 1, 7, 0, and 8. I would place the decimal between 1 and 7 because that's the only location that I could put it to where it would create a number that is between 1 and 10. So 1.708 is going to be that first value in my scientific notation value. So now I'm going to see how many swings does it take for the decimal at the end of my number to get between the 1 and the 7. So I'm going to streamline this a little bit. I know every time there's a comma that's 3. So this would be 3, 6, 9, 12, 15, 18. So that's 18 swings between the decimal at the end of the number to move to the 1.8. So again, with scientific notation, I have my number between 1 and 10. It's going to be times 10 raised to the 18th power because it took 18 swings to get from the end of the number to the 1.708. Now when we have really, really small numbers, we can notice in number 3 that my decimal is going to be swinging a different location. I already have the decimal to where I can see it, whereas in our larger numbers we have to remember that there's a decimal always at the end of those numbers. So if I want to find where to put my digit, I'm going to look at where do I have significant digits, where do I have non-zero numbers, and that would be at 162. So with 162, where can I put a decimal so that it's between 1 and 10? Well, that would be 1.62. So I know that I'm going to want to put my decimal between the 1 and the 6. I know for scientific notation that I multiply by 10, and then let's see how many swings does it take for my decimal to move from where it's located to where I want to move it to between the 1 and the 2. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 10 swings. Now notice, we're swinging a different direction than we were with our very, very large numbers. Since it's our very, very small numbers, this is going to be a negative exponent. And that's how you know if you're going to have a very large value or a very small value. If it's a positive exponent, usually that would result in a very, very large number, and if you have a negative exponent, it results in a very, very small number. So if we look at our last example here, I can see that I have significant digits 10003. So if I want to find a location to put my decimal that is between 1 and 10, I would put it between the 1 and the 0 if it lets me. There we go. So 1.0003. Again, scientific notation has to be times 10. And then how many swings does it take me to get from where the decimal is to where I want it to go? 1, 2, 3, 4, 5, 6. So it takes 6 swings, and that's going to be -6 for our exponent. Moving on, if we're going from scientific notation, numbers in scientific notation to standard form, I'm given my 9.3. I see that I am going to be swinging 6 decimal places to the right. So 1, 2, 3, 4, 5, 6. My new decimal will be at the end of the number. And what I need to do with all of these empty swings is I'm going to put zeros in there. So 9.3 times 10 to the 6th is actually the number 9,300,000. If I look at number 2, 4 times 10 to the 12th, so I start with 4 as my significant digit. The decimal is technically after it, and I'm going to swing the decimal 12 places to the right since it's a positive 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to fill all of those swings with zeros. Now be very careful to make sure you're not putting in extra zeros or you're missing swings. Okay, so that gives us 4 trillion. Okay, if we try number 3, I notice that I have a negative exponent this time around, so that means I'm going to be swinging my decimal to the left. So I'm going to actually be writing my significant digits more to the right of my box because I know that my decimal is going to be swinging left. So it's going to be swinging left 10 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My new decimal place will be there, and I fill all of my missing swings with zeros. And you'll notice that we now have an extremely small number. And then last but not least, I have 7.7 times 10 to the -4th. So again, my exponent is negative, so I'm going to start to the left writing my significant digits, and I'm going to be swinging my decimal 4 places to the left. 1, 2, 3, 4. Put in my new decimal. I fill my swings in with zeros, and I get the small value 0.00077. Okay, I want you to try the U-Try. When you're done, get it checked with an adult before moving on.